Okay, so this is now video 4 of our programmable systems and the use of microcontrollers. What we're going to look at in this video is how we use microcontrollers to detect and respond to inputs. So far, all we've done is control the state of outputs, just switching things on and off. And we've looked at, infinite looping, or we've looked at having a stop bubble at the end so the thing only does it once. And we've looked at, a counted loop, a finite loop. We've learned to do things a certain number of times. And all of those examples that we've done so far and the questions that we've done so far, the microcontroller has never responded to any input. And I know we've got a like in the start bubble, there's a play button, and some people, kind of mistakenly think that that's representative of something in the real world. That play button is just there for simulation purposes in Yenka. The reality is, if you make a flowchart, if you make a code, and you download it into a microcontroller, the microcontroller will immediately start running that code as soon as it's switched on. The microcontroller won't wait for a play button to be pressed. The microcontroller will start executing the commands as soon as you give it power. And that was why I was saying, if you use a stop bubble, if you've got a set of sequential code that runs and then stops, the only way the microcontroller will ever do that code again is if you take the power away and turn it back on again. As soon as you turn it back on, it'll immediately start executing that code again. So we're now in this video going to look at, right, how do we put inputs in here? So what I've got on the screen here is I've got a microcontroller with an input on it now. This is the first time I've used an input. And I've just got a switch. It's a latching switch. It's not a momentary switch. So I'll press it and move away and it stays pressed. You can see how you have to put a 5 volt supply going in. So essentially what we're doing is we're raising input 0 to 5 volts whenever we press this switch. This is good enough for National 5. This isn't actually how it's done in the real world. Hires learn that stuff later on. And I've wired what have we got? A red LED to output 0. So, just at its most simple, let's get a system in place where if someone presses that button, that light comes on. If you can do that, then you can make a system that will do quite a lot of things. So obviously we've got a start bubble. We start off with a start bubble. And the first thing we're going to do is detect this switch. So we use a decision symbol for that. And it's the test input decision symbol. So it looks the same. If you're doing it on paper, the symbol is the same as the test variable symbol. It's called a decision symbol. It's just drawn as a wee diamond. The interesting thing about decision symbols is they've always got two things coming out of them. And they should always be labelled Y and N. The only thing you can do in a decision symbol is ask a yes/no question, and you should always indicate what way the code is going to go if the answer is yes, what way it's going to go if the answer is no. This decision symbol says, is input 0 1? So obviously I can change that to any one of the 5 inputs. Notice on the 18M2 chip the inputs are numbered weird. 0, 1, 2, 6 or 7. I think it's just an artifact of the way these chips are put together and what the pins are used for. So I can change that to any one of those pins, and I can say is it on or is it off. I've got a bunch of other things in there with mathematical symbols. Again, at National 5 we don't use that, but we will at higher where we treat analog inputs slightly differently. So is input 0 on? If it is on, then I want to turn on output 0. So I'm going to go turn on output 0. Lovely jubbly. If it is off, what do I want to do? If it's off, I want to turn off output 0. And then after turned off, I want to go back to the start. Lovely jubbly. I'm going to make sure I'm on quick step before I go any further. Quick step. So now when I run it, well, in fact, actually, let's slow it down so that we can see what the microcontroller is doing. So when I run it, it checks to see if input 0 is on. Input 0 is not on, the switch is open, so the answer is always no. So then it sets output 0 off and goes back to the start and does it again, so that's why it's continually alternating between those two things. And then when I press the button, the answer will be yes and it'll turn it on. Nice one. The system works when I turn it off. It goes off. Now obviously it was a wee bit of a delay there between me pressing that switch and it going off, but that's because we're not on a realistic simulation speed. Put on a realistic simulation speed, it just seems to happen relatively instantaneously. Now that's one way to do it. There are many other ways to do it. So for instance, let's stop that flowchart. I could go, is input on? Yeah, put it on. And then once it's on, let's check and see if it's off. And if it's off, turn it off. So in this instance, if it's not on, it's not that I want to turn it off because I've got the off command. It will go off after it's been on. If it's not on, I just want to keep checking to see if it's on. I'm allowed to do that. I'm allowed to loop that decision symbol back into itself like that. That's called a polling loop. So it basically means that the microcontroller will get stuck there until the answer changes. And then down here, I'm wanting to see if it's off. And again, I can stick a polling loop in there. Both of those are equally valid. And then if it's off, let's just go back to the start. So this will do the same thing as the last one, just in a different way. So the output here will look the same. So I've slowed it down so that we can see the steps. You can see that the microcontroller is just stuck in there. When I press this, we'll move to this one and then get stuck in that loop. And then if I turn it off, it goes off and back to the start again. So functionally it's the same thing. Speed it up, make it a bit more realistic. On and off. So functionally you see the same thing happening, but we've got a different flowchart happening here. So we've got the flexibility to kind of think logically. So what's a solution for one person might not be a natural solution for the next person, and it's totally okay as long as you solve the problem, as long as this bit does the correct job, and that's the important thing. There are other things that we can do with inputs, like for instance, and again, by this point in the course, you should already have been exposed to the concept of logic relationships. So let's say, for instance, hold on, let me set this up. Right, so I just changed that so that the switches have got names, right? I've got switch 1 and switch 2. So in this instance, let's say, so suddenly I've got two different inputs, that I want the ready light to come on when switch 1 and switch 2 are pressed. How would I do that? So I'm going to have, let's get rid of that stuff just now. So I'm going to have a bit of code in here that is turning output 0 on. So that's how I turn it on. But I get there from switch 1, which is input 0, and switch 2, which is on pin 2. So to get to here, I need to go through this one and this one. Both switches have to be on. So in an AND, what we do is we chain them together. So this one is on, yes. This one is on, yes. And that gets us to our command that turns the output on. So that's what AND looks like. Obviously it's not finished yet because where the loops go. So obviously if input 0 is not on, we want to just keep checking. So nothing's going to happen until input 0 is on. And once input 0 is on, then we test this. Now, some people might have the inclination to do that for AND. If you think about it logically, let's test this one out. Yeah, let's just see if we can get the light to come on. Let's not worry about what the rest of the code looks like. Let's run this. Let's run it on full speed. So if I go input 0 on, notice the light doesn't come on. If I press input 2 on, yay, the light comes on when input 1 and input 2 is on. When I need to reset it, I can double click on the microcontroller to reset the outputs. And I can start this again. It doesn't come on when I press 2 because it's still checking the first one. If I turn that one on and then turn that one on, the light comes on immediately because as soon as that one came on, that one was already on. Just different wee games to play. Let's reset the outputs again. Watch this one. This should subvert your expectations. 1 on, 1 off, 2 on, 2 off. Oh, it didn't. What happened there? I didn't press play. That's what happened there. Yeah, so now that it's actually running, right? So let's run it. Okay. So 1 on, 1 off, 2 on. Oh, wait a minute. So the light's on even though 1's off and 2's on. That's not a true AND. And the reason it's not a true AND is because of that loop on that second test. The loop on that second test is getting caught in this polling loop. So the amount of time that could pass between that one going on and that one going off could be days. It could be days. So that's not any good for AND. So the truth is, a proper AND would always loop back to the start in all cases. Yeah, so now that won't happen. So 1 on, 1 off, 2 on, the light doesn't come on. It'll only come on both on at the same time. Now don't be wrong, it is possible to fake it, but you'd need to be faster than 4 microseconds, and you're not going to be faster than 4 microseconds. So that's AND control. The other most obvious logic control that we use, or the most common, is OR control. So let's say we want this light to come on when switch 1 or 2 is pressed. It's just a slightly different arrangement of these decision symbols. There are two possible paths. There are two possible paths into that output or 0 on bubble, and the two possible paths are from here or from here. So we can get into here if this one's on or if this one's on. So if this one's not on, we want to check that guy. And if this one's not on, then we just want to go back and check that one. So what we've got now is a polling loop with 2 tests in it. So if I slow this down, we'll see the polling loop. And it's checking the 2 tests over and over again. And if the answer to either one of them is yes, then we get down here. Doesn't matter what one I press first, the light will come on. So that's what OR control looks like. So we've got AND, and we've got OR. Just move this up here, put AND in here. So that's the ways that we can treat inputs. You know, just having an input that controls an output, whether it's on or off, and you've seen it done using a polling loop on it as well. And then we've got AND control. I've labelled it AND control, and that one's OR control. You might want to take a note of that to try to remember what one's what. Okay, so what I'm going to do now is just set up a couple of specs and ask you to create a flowchart that meets that spec. And it's going to be the same deal. It's going to be a microcontroller with outputs that you have to create a flowchart for. In some cases, it will just be switching something on. In some cases, it might be switching something off. And in other cases, there might be heavy AND control. It would be 3 or 4 questions. Let's see what I can come up with. Okay, so here's the 3 questions that we're putting in this document then. So the first one, you can read the spec. The system is to display either a green light or a red light. The switch alternates. That's supposed to say alternates between red and green. So again, there's only one input, but there's 2 outputs this time. So if the button's off, and you can choose, it doesn't matter what one it is. When the button's off, I don't mind what light is on. So if it's off, let's say it's the green light, and if it's on, it's the red light. It's very similar to the added. And the second one here, this is the control system for a lathe motor. The motor should only spin if both switches are on. So that's AND control. The system should be reusable. There should be no stop bubble in there. Again, very similar to the AND control example that I've already shown you. This is the control system, the last one. This is the control system for doors on a train. The doors are operated by a solenoid if either switch is pressed. So this is OR control. The solenoid should actuate. The door should close on its own. A buzzer should sound while the doors are open. And I'm going to let you decide whether you think this system uses a stop bubble or whether it's looped infinitely. So this document is called Microcontrollers Detecting Inputs, and you'll find it in the people share. It's got the original examples still in it, but you've got them in the video anyway. As always, make sure that you complete this exercise and show your teacher the answers.